So, my name is Iori Mizutani, and I am a doctoral researcher at University of St. Gallen. In this talk, I will introduce the explainable industry automation from both industry and research perspective. A little bit about myself. I studied research in the automatic identification domain 7 years ago in Japan. And in 2018, I moved to Switzerland to do my PhD at HSG with interaction and communication-based systems research group. Since last year, I have become a member of Untitled Labs in Switzerland. And here I am talking because the Untitled Labs have been collaborating a lot with GS1 Switzerland, right? What I'm going to talk about today is first some problems in the current industrial automation systems, abbreviated as IAS, then have a closer look at those challenges, especially for semantic interoperability. And in the last part, I'd like to introduce you Web of Things toward explainable IAS. Industrial automation systems. To begin with, I will show how automatic identification is relevant across the entire supply chain. This image is taken from a proof of concept project in the past in order to give traceability information from the supplier to the shelf in the convenience stores using RFID. We all know that if we can track a product for its entire trajectory in the supply chain, everyone will be happy because we can extend the value chains in many directions in the ecosystem. In today's talk, the focus will be more on B2B domains among suppliers and operators in the logistics pipeline. In the logistics pipeline of IAS, one thing that we should always be aware is that we need to deal with multiple identifiers for different things at different levels. Let's take an example from a metal part supplier, Louise and Diana. In the factory, the production starts from a metal rod, which has a proprietary ID called melting point number that is associated with a material profile and certificate documents provided by the metal provider. In the next step of manufacturing, the rod is cut into smaller sizes and polished. Notice that at this point, the melting point number is also washed away, and we cannot find them on the surface anymore. After processing the rod into an actual part, the part gets an ID, but they are often, again, proprietary IDs because they are just used for a long time and already associated with other article and rod numbers. These non-standardized IDs create problems such as how do we trace all the way back to the source material, or is it possible to track individual physical object if it is literally not possible to attach any ID on it? Let's move on to the next level. From the item level in identification, we can use various data carriers to identify objects as needed. In the IT infra of GS1 systems, the data capture is done at the bottom layer. So that the captured information can be used in the service applications like EPCIS, and we can possibly send high-level queries. Where is my item? What's the status of my order? And does it have a proper certification? These queries require the system to trace all the way back to the source material. And to find a document associated with it, the kind of effort is particularly important nowadays due to the recent political movement like Konzern Verlautungsfundungs initiative, and it might even become a mandatory regulation in the future. All right, but in this picture, there is one more thing we need to discuss. That is how we actually operate and control the field devices in the system, like RFID readers. In the next slide, I will show you why do you really care about these when we think about the business value chains. The metal part supplier produces the artifact with industrial equipment like this turning machine. Inside the turning machine, for example, the metal rod is processed with a spindle and a cutting blade. This cutting blade is a consumable supply, and the wearing must be compensated to maintain the process accuracy. But it also needs to be replaced by humans, and you might guess this is not small expenditures for suppliers. And meanwhile, the machine is controlled by software, In the display, each line represents the movement of milling header, and surprisingly, it is based on the legacy systems that have traditionally used punch card straight for this command. Why am I showing this? It is because if we can somehow combine this hard to understand control sequence and inventory information together, we can find an optimal solution for operators, such as when is the best time to replace a cutting blade to maximize profit. To summarize what explainability contributes to business values in IAS, I try to put them into 4 major categories. The first one is interoperability, to avoid vendor lock-in and also to provide a cross-domain information exchange. The secondary, the traceability. This is to provide visibility of items throughout the entire supply chain. Accountability adheres for security and safety requirements and potentially future regular compliances. Finally, the transparency gives clear decision-making process and also to reveal and focus causality in industrial automation systems. In the first part, we saw why we need explanation for IAS. In the next part, I want to show why it is not that easy to give explanations by defining the semantic interoperability. Let's take a step back and think about the industrial IoT. On one hand, the smart home, the home automation can be built with equipment in an affordable price range. And you can append as you prefer or to meet your own comfort, buying Philips Hue bulbs, getting Google Home equipment, and etc. On the other hand, smart factories often start talking at $1 million and beyond. Furthermore, most of the cases, it is a replacement of older appliances, which are also heavily integrated into the shop floor and involves migration cost. In the design phase of automation systems, it is effortless to think that the new enhancements can solve everything, but we can never underestimate the migration cost, especially if you need to maintain the compatibility with existing assets and flow of operations. In the next slide, let's have a closer look at how the IAS operate. IAS have a common architectural style called automation pyramid, and it consists of 3 to 5 layers. The top layer is ERP, Enterprise Resource Planning layer, that coordinates the most business-related tasks such as order processing, financial asset allocation, long-term production planning, and so forth. This is not so specific in the automation industry, so I assume most of you are kind of familiar with it already. The next layers are Mes and Scada. The responsibility of these two are slightly different from each other, but we often treat them together. The basic functionality is to interpret a business level objective, such as we need to produce thousands of a certain metal part for customer by next week. And then the MES, manufacturing execution system, composes an operation planning for machine learning, machine level instructions. This layer also accounts for monitoring the status of shop floor and processor data retrieved from the sensors and actuators. For example, it checks if there is a chance of causing fire due to overheating. Lastly, the bottom layers are for controlling and operating physical machines. Again, these two layers are usually viewed as one, and in this layer, specific instructions are passed down from the upper layer, and the machine devices process the tasks. And please note that the hierarchy we've seen in the logistics pipeline in the previous part is orthogonal to this pyramid particle segmentation. They are all physical objects, so it's on the field level layer. To understand the semantic interoperability, please bear with me for a little more details. And the modern IAS employs so-called service-oriented architectures. That is to make it a scalable system, dividing each responsible unit into services. It is great we know who is responsible for what. However, this is creating the complex interdependency among the service, and it is quite challenging for us to comprehend the flow in the system because the service resides in the different layers. For example, the ERP receives an order from customer, configure the MES service, and start a production cycle. In this case, the explanation we need is the production line X is operating under Y control in MES, which are initiated by the order Z at ERP system. And this is what I call semantic interoperability of IaaS. And naturally, this is the future IaaS should be explainable to different stakeholders. This is the systemic overview of the modern IaaS. Now, in the last part, I'll show you how we can actually implement the semantic interoperability with Web of Things. Web of Things is a standardizing effort in W3C to aim for enabling interoperability across IoT platforms and application domain. The core idea is that the web has been one of the most global systems on this planet, and therefore it has many practical principles we can apply to design a sophisticated systems like IaaS. One key enabler that I want to mention is the thing description. Thing description can convey metadata in interfaces of things, where a thing is abstraction of a physical or virtual entity. And it can be described by its behavior, how we can interact with it, and what protocol it speaks. I will now show you a practical example for thing description in the GS1 context. GS1 Digital Link is a simple but powerful method to bring GS1 identifier into the web. For example, we can represent the SGTIN of a product in the URI like this. What we can do with this is, since this is in URI format, we can link this digital link with other metadata from different information sources, including thing description and even entirely different systems like EPCIS. Concretely, in the example scenario from part 1, if we put thing description for everything we are interested in, we can then form the web of things and can become a foundation for semantic interoperability. Furthermore, there is one interesting trend for automatic data capture in GS1 context, the operational control of RFID readers. LLRP, low-level reader protocol, is a GS1 standard for managing and accessing RFID readers. Recently, a joint call to action has launched together with RAIN RFID Alliance to revise LLRP. Among RFID vendors, they have implemented custom vendor extensions in the readers, so the new version aims to reduce the vendor barriers and alleviate the vendor lock-in for both hardware and software. More importantly, the RAIN has been developing the new interface for the readers, and that is web-friendly. So that Web of Things integration will become a lot easier for GS1 data carriers. To summarize, industrial automation systems are becoming increasingly complex and requires explanation. The current industrial systems lack the semantic interoperability to extend the value chains, and the Web of Things can interconnect things, and it aligns well with the recent organization effort. Thank you for watching the video. If you have interesting problem, I would love to discuss more with you in the detail. So please feel free to contact me. This was Iori Mizutani. Thank you. Bye-bye.